The next topic under optics is total internal reflection. This is chapter 5.3.2. By the name itself, you should be able to figure out what we are going to learn in this subchapter. Total internal reflection. So it is a reflection within the material itself, because it says total internal reflection. Total internal reflection. Now we will learn this in detail later, but from the name itself you can figure it out. So something is totally reflected within the material. This is what we mean. And the material is a denser material compared to the material that is surrounding it. For example, the material can be glass and surrounding the material can be air. So you see, the surrounding material is rarer. Rarer means less dense than the material that we are going to consider when it comes to total internal reflection. By the end of this section, you should be able to understand that waves can be reflected and transmitted at an interface between media. Now interface is the boundary. For example, over here this line is separating the two mediums or media. Say this is glass and this is air, for example. Then this line is the interface. Interface also called boundary. Also we can say this is the surface of glass if this material is glass and this material is air. Understand the term critical angle. Now when it comes to total internal reflection, you have to understand that when the angle of incidence is greater than the critical angle, total internal reflection occurs. So what do we mean by the critical angle? For different materials there are different critical angles. For example, if you consider this material here, let's say it's glass, it also has a certain critical angle. Now here you can see theta I. By the way, this is a Greek letter. I think I have created a separate video explaining the Greek alphabet. You can go through that. I am explaining the letters of the Greek alphabet. So if you go through that video, you will have a good understanding of the Greek letters, because we use a lot of Greek letters in physics. And if you understand that video well, you would also become to a certain extent you would become literate in Greek, okay, because I am telling you the letters, all the letters of the Greek alphabet, and the pronunciation is normally like English, like the first the sound of the English letters, it's similar to the sound of the English letters. So if you know the meanings or the names of the letters, then the first part of that name is like the pronunciation, and you would be able to even read Greek if you go through that video. And it will also help you in physics, like I said before, because we are using a lot of Greek letters in physics. Now here we have theta I is less than theta C. Theta I is less than theta C. Okay, so what is I? I is the angle of incidence. If this angle of incidence is less than the critical angle, okay, what do we mean by the critical angle? When the angle of incidence is equal to the critical angle, like you see here, the refracted ray, this is the refracted ray, this is the incident ray, this is the incident ray, this is the refracted ray. You learn this when you learned about refraction, the angle of incidence, the angle of reflection, the angle of refraction. Always these three angles are formed between their ray and the normal. For example, this angle here is the angle of incidence or the incident angle, because it is the angle between the incident ray, and the normal. Whereas this angle here is the angle of refraction. It is the angle between the refracted ray and the normal. What you have to remember here is this angle here is now the critical angle, because when the angle of incidence is the critical angle, you will have the refracted ray going along the interface. Remember what the interface is? It's the boundary between the two materials. So over here I equals the critical angle. The angle of incidence is equal to the critical angle. By the way, like I said, this blue material is the denser material. Now if you look at the third diagram, so far we saw when the angle of incidence is equal to the critical angle, when the angle of incidence is less than the critical angle. That's the first image, when the angle of incidence is less than the critical angle. The second one is where the angle of incidence is equal to the critical angle. Now what's the third possibility? When the angle of incidence is greater than the critical angle. That's what we have here. Angle of incidence is greater than the critical angle. When the angle of incidence is greater than the critical angle, you have total internal reflection. Now here you have refraction, and also to a certain extent you can get reflection as well. Okay, but over here you don't have any refracted ray anywhere. So entire thing is reflected. That's why we say this is total internal reflection. When the angle of incidence is greater than the critical angle, you will not have any refraction, you will have only reflection. This is total internal reflection. Again, by the name itself you can figure it out. Total internal reflection. So you see, it's internally within the material, the entire thing is reflected. So this is an example of total internal reflection. You have to remember that total internal reflection occurs when the angle of incidence is greater than the critical angle. When the angle of incidence is equal to the critical angle, you have refraction, but there is no refraction in the second medium here. It doesn't go into the other medium. Instead, the refracted ray goes along the interface. Over here, you will have refraction, and to a lesser extent, you can also have reflection. Now, let's look at the instance in a real situation. For example, over here, this is the first case. You see the first diagram here? The angle of incidence is less than the critical angle. That is what you see here. By the way, this is a semicircular solid glass block. If you have seen this in the physics labs, you all would have also seen the experiment or the demonstration of this. So what we do, we have an incident ray that is striking the circumference of this semicircular glass block. What do we mean by semicircular? Semicircular means it's half of a circle. Okay, this is a solid semicircular glass block. What do we mean by solid? The opposite is what? Hollow. So the inside of this is not hollow. Hollow means it's empty, it's air inside. It's not hollow, it's solid. Solid means it's also filled with glass. So the entire thing is solid glass. It's not empty inside. That's what we mean by solid. So this is a solid semicircular glass block. We have an incident ray that is striking the circumference, that is over here, the curved surface here, perpendicular to it. Okay, it's coming, in other words, along the normal. So when it comes along the normal, even though it goes from one material to another material, there won't be refraction. It doesn't change direction because it's coming along the normal. Now what happens here is that it strikes the middle of this semicircular block. So this, in other words, is along the radius of the semicircular glass block. Remember, what is the radius? The radius joins the center to the circumference. Therefore this incident ray is going from the surface to the center. So it strikes the center of the semicircular glass block. Now what happens? Since the angle of incidence is greater than the critical angle, is less than the critical angle, that is this case, there is refraction. And by the way, when you learn refraction, you learn that when the ray of light goes from the denser medium to the rarer medium, rarer means the less dense medium, it bends away from the normal. It bends away from the normal. Okay, so in this case, the angle of refraction is greater than the angle of incidence. Always when the light ray goes from the denser medium to the less dense medium, the ray bends away from the normal. Therefore the angle of refraction is greater than the angle of incidence. So that's why we have a refracted ray instead of this situation or this. So the angle of incidence here is less than the critical angle. Therefore you have refraction into the other medium. Here it's air. This is only glass. So the surrounding is air. Now in addition to that, like I said before, you will also have reflection. You will also have reflected ray, and that is this. You can see this is the reflected ray. Then what happens now, if you continue to increase this angle of incidence, then this situation will happen. And if you still continue to increase it where it is greater than the critical angle, then you won't have a refracted ray here, you will have total internal reflection. Moving from refraction to total internal reflection, you can see that in the three diagrams here in figure B. So this is about total internal reflection. Now let's go through this also, so you can try this if you can purchase this or have access to this. And I usually do this with a laser. You can also have a normal light inside a box with a slit, then you will have a beam like this. But it's easier if you have a laser, but be careful, don't point the laser at anyone's eyes. So you can have the laser and you can see this happening with the laser. It's much easier. When waves pass from one medium into another, some waves energy will pass through and some will be reflected. So pass through, it's transmitted, in other words. Then we have reflection. The proportions will depend on the amount of refraction and the angle of incidence. So that's what I told you about these angles of incidence. Partial transmission and partial reflection. So you see, partial transmission, partial reflection at a media interface. Interface means at the surface. So you can see where the boundary is between the two materials, that's called the interface. And this happens, the refraction and reflection happen at the interface. In the diagrams of figure B, we can see a ray of light trying to leave an optically more dense medium. So for example, it can be glass, here it can be air. In these examples, the partial reflection is not drawn. You can see it's not drawn here, but you can see it in the picture here. The first diagram shows simple refraction. You see, simple refraction, for which we could use Snell's law. What is Snell's law? Snell's law states that the refractive index is sin I divided by sin R. Now when we apply this equation, you have to keep in mind that the ray is going from the rarer medium to the denser medium. So sin I divided by sin R is equal to the refractive index, and that refractive index is of the denser material. Let me show you another diagram to help you understand this better. So I will switch books right now. And by the way, this is the O-level book. I have explained this to you in the O-level or IGCSE classes. You would have seen this lesson on light and rays, waves. Okay, and this is on total internal reflection. By the way, I have noticed that several O-level and IGCSE students even have a lot of questions on this topic. So let me quickly go through what we already saw, and you can see that in these three diagrams also. You see here, this is the angle of incidence, this is the refracted ray, and you also have a reflected ray. So here the angle of incidence is less than the critical angle, but over here we can move this lamp to the left and the light is still falling on that same position. The dashed line is called the normal. Normal is always perpendicular to the surface, and we draw it as a dashed line. Now when the angle of incidence is equal to the critical angle, what will happen? The refracted ray won't go into the other medium. Instead it will go along the boundary or the interface or the surface of air and the surface of water in this case. And remember, we have always the denser medium in which we have the incident ray, and the point of incidence, that is where it strikes the surface, is where we have the refraction happening. But it has to be within the denser medium for you to observe total internal reflection. Over here, the angle of incidence is greater than the critical angle, therefore there is no refraction, everything is reflected. Therefore we call this total internal reflection. And you can see here, I equals angle of incidence equals critical angle, angle of incidence greater than the critical angle. And they all have also given you the values of critical angles for different materials: water, acrylic, plastic, glass, diamond. Now let's go into the Snell's law part. Now in the O-level or IGCSE classes, this is what you learned. The Snell's law. The refractive index is equal to sin I divided by sin R. And these are two equations that you learn for refractive index. This is what you learned in the IGCSE or O-level classes. But in the A-level class, instead of just saying this is refractive index, we will see a little bit more to this refractive index. Okay, so here we can simply write this like this or like this. We just have just one n equals sin I over sin R, and we will see why we have 2 there in the O-level class, in the A-level class, because here we consider this going from air to the material. Air, yes, we simply use this with just n instead of n1 and n2. Now what do we mean by n1 and n2? I will explain that also. The refractive index is speed of light in vacuum divided by speed of light in medium. So if you consider speed of light in vacuum and the speed of light in the medium, if the medium is air, for example, so vacuum and air have almost the same speed, 300,000 kilometers per second, or 3 into 10 to the power of 8 meters per second. This is the speed of light in vacuum, which is almost and effectively the same in air. So these two are almost the same. That's why the refractive index of air is 1. And when it is 1, since this is going from air to glass, we can say the refractive index of the material n is equal to sin I divided by sin R. But this can be used if the ray is going from air to the material. But if it is between two other materials, then the refractive index is not 1. You will have to consider that in this calculation. Now in the A-level class, we will see this in detail. So you have an n1 and an n2. Okay, so here in the O-level class, you simply had the refractive index n sin I over sin R, because the refractive index of air is 1. So that's why you don't have the second n there. But this is the most correct way. See, we have this. Now again here the angle is 90 degrees, so it will become 1 here. That's why we have this. But we will understand this better by going through some examples. This is what you saw in the O-level class. So here it's air, here it's glass. Sin I over sin R, we have the Snell's law. Angle of incidence, sine of that divided by angle of refraction. This will give us the refractive index of glass. Okay, now let's go to the explanation here. In the diagrams of figure B, we can see the ray of light trying to leave an optically more dense medium. So you see the denser medium, I told you. It's trying to leave the denser medium. It's trying to leave from here the denser medium. The first diagram shows simple refraction, for which we could use Snell's law to make some calculations. The angle in the less dense medium is greater than the incident angle inside the more dense medium. Okay, so here you can see this. The angle in the less dense medium is greater than the incident angle inside the more dense medium. So you can see clearly what that means is the angle of refraction is greater than the angle of incident angle is this. Angle of refraction is greater than the angle of incidence. That's what this means, because when you go from a denser medium to a rarer medium, it bends away from the normal. The ray bends away from the normal. In the second diagram, the incident angle has been increased. So you see, we increase it so that the angle of incidence is equal to the critical angle. From Snell's law, we find that at this critical angle, the ray would emerge in the less dense medium at an angle of 90 degrees. So it doesn't really emerge, but it goes along the normal. So this angle here, angle of refraction, is now 90 degrees. Angle of refraction is the angle between the normal and the refracted ray, and that is 90 degrees here, when the angle of incidence is equal to the critical angle. In the second diagram, the incident has angle. From Snell's law, we can critical angle would emerge in the less dense medium at an angle of 90 degrees. It would emerge right along the interface. So there is a refraction, but the refracted ray goes along the interface. If the angle within the more dense medium is increased further, the emergent angle should also increase. But this would then be greater than 90 degrees, which means the ray emerges within the more dense medium. So you will have this. So this is not refraction, as that requires a change in the medium. This means that Snell's law cannot apply. So in total case of that, they are talking about this case. So if you continue to increase this angle of incidence, the angle of refraction will increase, and it will come to a point where the angle of refraction is 90 degrees. But if you still continue to increase this angle of incidence, that is more than if you try to increase more than the critical angle, then you will have total internal reflection. It would emerge right along the interface. Okay, we read that, which means the ray emerges within the more dense medium. This is not refraction, as that requires a change in medium. This means that Snell's law cannot apply. So Snell's law should apply when there is an angle of incidence and an angle of refraction. In this case, what does happen is all the wave energy is reflected inside the more dense medium, and the angles follow the law of reflection. This is total internal reflection. Alright, so let's go through the calculations now. Critical angle calculations. From Snell's law, we could find the critical angle for a material. So this is the equation. N1 sin theta 1 equals N2 sin theta 2. Very easy to remember. Here you have all ones, N1 and sin theta 1. Here you have all twos, N2 and sin theta 2. If we take medium 1 to be the optically more dense material, then theta 2 must be 90 degrees. So this is the more dense material. This angle is theta 1. Here the angle is theta 2. This is the second medium, the rarer medium. In other words, it can be air here. Here it can be glass, for example. If we then take medium 1 to be the optically more dense material, then theta 2 must be at 90 degrees. When the light is at the critical angle theta c in medium 1, theta c in medium 1. So in medium 1, that is the denser medium, that is this case they are talking about. Okay, the angle of incidence is equal to the critical angle. If we take medium 1 to be the optically more dense material, then theta 2 must be 90 degrees when the light is at the critical angle theta c in medium 1. So we have N1 sin theta 1 equals N2 sin theta 2, N1 sin theta c, first angle. Now angle of incidence is the critical angle. Now when the angle of incidence is the critical angle, theta 2, which is the angle of refraction, will be 90 degrees. Okay, then we have N1 sin theta c, and remember this is 1. See, that's what's written here. Sin 90 is 1. So we can now write 1 there, but 1 times N2 is N2. So we have N1 sin theta c, then sin theta c equals N2 over N1. N2 over N1. Now let's say this material here, the second medium is air, then the refractive index is 1. For air, refractive index is 1. If the situation involves a light ray emerging into air, then the equation becomes this, because the refractive index of air is 1. So N2 is 1. Then we have this equation. If we know the critical angle, then that will give us the refractive index for the material. So if we know the critical angle of a certain material and we assume the ray is the surrounding is air, then we can find the refractive index. So if it is surrounded by air only, you will get this equation and you can find the refractive index. If we know the critical angle, then that will give us the refractive index for the material. So we can use this equation, n1 equals sine theta c. So this is the equation. Now remember, in this case n2 is equal to 1. n2 is equal to 1 because n2 is the refractive index of air. The outside material, n2, or the second material, okay, 1 is for the first material, 2 is for the second material is air. Then only you can use this equation. Okay, so this is the same experiment I was talking about here. So you can see, can you see, this is half of a circle here. This part is empty, can you see? This is the glass. Here there is no glass, so the semicircular glass block is here. They have drawn two lines here, and by the way, there is a video explanation on this. So for the students who buy the complete Edexcel IAS Physics course, will have access to these video demonstrations, experiments, all of that. So I have posted the link in the course so you can watch the experiment. And by the way, this is what you have for unit 3, the practical paper. So make sure you watch the video if you're taking the online course, or if you purchase the online course, you will have access to this complete explanation, the experiment, how this is done, where we draw the lines and all that. So you see, this is a laser, or it can even be a light sent through a slit, so you have a beam of light, and this should strike the center of that semicircular glass block, and you can see the normal is drawn like this with a pencil right at the center of, it's passing through the center, or the center of the glass block, we can say, this point here. And here this is coming along the radius, so it gets reflected, and this is also going along the radius of that semicircular glass block. Using a setup like that shown in figure C, so investigating total internal reflection, what you can do is, if you look at the experiment video, you will understand everything here. Now if this angle here, which is the angle of incidence, is less than the critical angle, then you will have some refraction here. But if in this case, you see here, the angle of incidence is greater than the critical angle, therefore there is total internal reflection. And by the way, there is no refraction here or here, because the ray strikes this boundary, this interface, perpendicular to it. Okay, it's coming along the radius. Remember, radius and circumference of a circle are perpendicular to each other. So this comes along the radius. This is 90 degrees, so it passes straight through without any refraction, even though it's going to the other media. Using a setup like this shown in figure C, we can steadily increase the angle of incidence, theta 1, with the more dense glass. So you see, this is inside this, so we can increase the angle of incidence. And observe the emerging angle of refraction, theta 2, that is this angle, in the air. As the angle inside the glass increases, we shall see a partial reflection of the ray within the glass growing stronger in intensity. So we start with a small angle, and you will also see refraction. In that case, you will see something like what we saw in the picture here. But when we gradually increase this angle of incidence, and when the angle of incidence is equal to the critical angle, the refracted ray goes along the interface, and if you continue to increase that, you will have total internal reflection, no refraction. As the angle inside the glass increases, we shall see a partial reflection of the ray within the glass growing stronger in intensity until the critical angle is reached inside the glass. So if you keep increasing the angle, the incident ray is as it is, but the refracted ray becomes less, the reflected ray becomes stronger. So that's what they are saying, reflection of the ray within the glass growing stronger in intensity until the critical angle is reached inside the glass. And after the critical angle, if you continue to increase the angle, you will have total internal reflection. Very simple to understand. measuring angle of incidence and refraction in order to find the critical angle and refractive index for glass. So this is the equation. Refractive index of glass equals 1 over sine the critical angle for glass. Now again remember, you can use this if it is going from air. So the surrounding should be air, because the refractive index of air is 1. Then only we can get this equation with a 1 there. And also the ray has to pass along the boundary, because then we have sine 90, that will also be equal to 1. Therefore we get this equation. The block should be an exact semicircle. So we have a solid semicircular glass block, and we aim the ray to travel through the glass and hit exactly the midpoint on the flat side. So I already showed you that on the flat side we hit the midpoint, the center of the semicircle. This means that ray passing through the glass will be traveling along a radius of the semicircle and will have entered the glass. So you see, along the radius of the semicircle, entered the glass here, exactly along the normal to the circular edge. So the only change in direction occurs at the flat side of the block. Okay, so here flat side of the block, flat side, this side. Okay, this side is curved, this side is flat. So here we have the curve from here to here, flat curve, this glass block. Okay, okay, so the only changes the flat side. By carefully recording the critical angle when the light images, we can calculate the refractive index for the glass. So I already explained that. Now what are the applications or uses of total internal reflection? We can use this in an object called the periscope. From a periscope, using a periscope, you can see objects at a higher level from a lower level. You see here, this is a periscope. This is an instrument for looking over obstacles. Prisms reflect the light, you see, although they can be replaced with mirrors. So instead of prism, you can also have a mirror here. Now by the way, we use periscopes in submarines. You know, the submarine is going underwater, it can put its periscope up above the surface of water and see what is happening above the surface of water when the submarine is in the sea. Then we also have rear reflectors. Sometimes certain motorcycles or even bicycles have these rear reflectors, and even traffic signs you would have seen, they may also have this. But this is especially there in the bicycles, even in the motorcycles. So what happens is, when light falls on it, it gets totally internally, you will have reflection. Okay, you will have reflection. Now here you have total internal reflection inside the prism, and here also. So you'll have something like that here as well. Then here also you have total internal reflection. These are all reflecting prisms. These are called prisms. What is a prism? A prism has a uniform cross section along its length, and these are triangular prisms. So the cross section is always a triangle of the same dimensions, same area. Okay, so here you have a prism, a triangular prism. Figure D shows the movement of light through 45-degree prisms. The left hand example is commonly used in periscopes, and the right hand diagram is the fundamental basis for reflective science. Okay, so you have this. So this is actually used where? Here, reflective science. See, there you have that. Okay, so the prism is here. Then here we have this case over here, just one there. Here it's coming back to the same side, but here it's changing direction by 90 degrees. whereas here it's changing direction by 360 degrees. It's coming back to the same side. Same here. So this angle is 45 degrees. I plus R is 45 degrees. And by the way, the angle of incidence is always equal to the angle of reflection. That is one of the laws of reflection. Always the angle of incidence is equal to the angle of reflection. A more complex use of TIR is in fiber optics. I think here you can see, and also this I think has a picture. See, fiber optics. You see, you can also use that in an endoscope and in communication for transmitting information. This may a thin glass fiber can guide light along its length by repeated TIR at the internal edges, and I can see this picture shows that very clearly. So you have here a denser material inside. There is no air inside. Denser material inside, and outside you have a rarer material. I mean a material with a less optic density, optically less dense material. Inside is a optically denser material. Let's see. A more complex use for TIR is in TIR means total internal reflection is in fiber optics. A thin glass fiber can guide light along its length by repeated TIR at the internal edges. This may just be used for decorative lighting. So for example here, so this and this we can say is the same. So here it's a single optical fiber in the type shown above. The inner glass core is coated with glass of a lower refractive index. So the outer glass is having a lesser refractive index, inside glass is having a higher refractive index. So it's more dense, also we can say denser. Inside material is denser than the outside material. Then only you can have total internal reflection within that material, because it has to strike a less dense surface at the interface for total internal reflection to occur. Okay, so for lighting, but on a larger scale, can be used to guide sunlight to the interior of large buildings. Alternatively, optical fibers can be used to carry information as light pulses, as in fiber broadband optic fibers, or as actual images in uses such as medical endoscopy. See figure E, this one, and the photo for that is shown here. See, this is another example where we use total internal reflection. This photograph was taken through an endoscope, an instrument used by surgeons for looking inside the body. An endoscope contains a long thin bundle of optical fibers. So the light can be sent inside, and then you can have a camera fixed to this. That's how they took this photo. Or you can even see it live, what's inside. I have seen videos. Maybe if you go online and check endoscope, you might see this, how they see inside the gut, inside the digestive system. See, eyepiece, light from source. See, you have total internal reflection inside these optic fibers. So objective lens, and you can see reflected light from object. Eyepiece. A medical endoscope is used to weave the body's internal organs without cutting the patient open. Light is sent in along one optic fiber, and the reflection is carried away along the other for viewing by medical staff. Okay, that's the end of this lesson. Make sure you answer all these questions, and the definitions are also very important. You see, in the exam paper they can ask you to write what is critical angle, what is total internal reflection, what is the angle of incidence, what is the angle of reflection, what is the angle of refraction, what is the incident ray, what is the normal, what is the refracted ray, what is the reflected ray. So you have to be familiar with all these applications or uses of total internal reflection. We saw several uses: endoscopy, optic fibers, periscope, rear reflectors, binoculars, You know, binoculars are used to see objects far away. Again, if you are not familiar with some word or what a binocular is or what endoscope is, you can always Google it, or you can search it on YouTube. You might have a very good explanation of what endoscope is, what periscope is, and whatever you want binocular, you can see the details. The critical angle is the largest angle of incidence that a ray in a more optically dense medium can have and still emerge into less dense medium. Beyond this angle, the ray will be totally internally reflected. I already explained this. Total internal reflection, TIR, requires two conditions to be met. The ray is attempting to emerge from the more dense medium. So as told you, the incident ray should be in the denser medium and striking the boundary from the denser medium and try to go to the less dense medium. So we increase the angle of incidence to be more than the critical angle, then you will have total internal reflection within the material or denser material itself. The ray is attempting to emerge from the more dense medium. The angle between the ray and the normal to this interface is greater than the critical angle. Remember, I told you these things already. Okay, then that's the end of that lesson, chapter 5.3.2, total internal reflection. So here you learned Snell's law, you learned critical angle, and you learned how total internal reflection occurs. It was also explained under the key definitions. Then you saw some uses of total internal reflection. You saw how to find the critical angle, the experiment, and I told you you can watch the video explanation of this. So make sure you go through all that. And that's the end. Now next lesson we will see lenses. By the way, this entire physics lesson is available online for purchase. You can see the link in the video description, or you can also contact me, but if you go to the video description, there is a link for the complete Edexcel IAS or IAL Physics course. Click the link and you will go on to another website where you can purchase the complete course. You can also contact me and I can provide an alternative way of purchasing it, especially if the payment gateway is not available in your country. So this course can be done from any part of the world. Theory lessons are recorded and uploaded in the lesson. We have notes, we have tutorials, explanations for them, solved past exam papers with explanations to each question, and I can also include some live one-on-one sessions. Even this class is a live one-on-one session that I am conducting to a student that I have never met, who is living in another part of the world, and this student bought my complete one of my complete online courses. So if you all want, you all also can do that, and we can discuss past papers. We can have one-on-one sessions to discuss any difficult theory lessons, topics that you want to discuss. Okay, I hope to see you all soon in a live one-on-one class, and I also hope to see you all in the next video. Next we will discuss lenses.